Now, gradiometric BVP or boundary value problems. What is gradiometry? So far we have seen when we measure the geoid height, it means that we are directly measuring the potential. Or when we measure the gravity anomaly or gravity disturbance, we are actually measuring the derivative of potential. So we have the derivative of potential as a boundary value. And when we use astrogeodetic deflections or vector gravimetry, we have also horizontal derivative of the potential as boundary values. But what is gradiometry? You know, I define gravitational tensor. Gravitational tensor. This tensor is in fact 3x3 matrix, and we have the second order derivatives of the potential here, xx, xy, and xz, t, yx, t, y, and t, yz, t, zx, t, zy, and t, zz. So, as you see, they are the diagonal elements, and they are off-diagonal elements. So, if you hear somewhere that it is called vertical gradient, don't be surprised. Vertical gradient. Because Z is vertical, it means that along the radial direction towards the Earth center or outward from the Earth center. These are called plus this one, horizontal gradients, because they do not have any zeta in the indexes, no derivative with respect to zeta. And here you see zeta and zeta, and they are called vertical horizontal gradients. Note that these quantities are equal. It means that this matrix, this one is equal to this one. This matrix is symmetric. So when we measure these derivatives or measuring the gravitational tensor, then we say that we are doing gradiometry. Therefore, gradiometry means to measure the gravitational tensor. So gradiometry is when we measure the gravitational tensor. One important properties of this tensor is that the summation, the summation of the diagonal elements, I write it here, summation of the diagonal elements is 0. This means that this tensor is traceless. because T is harmonic. T is harmonic, or the potential is harmonic. It means that it satisfies the Laplace equation. In fact, this trace is Laplace equation. Laplace equation. So any function which satisfies this Laplace equation is called harmonic. So gravity field of the Earth is harmonic outside the Earth. So now I define another type of spherical harmonics, which are called tensor spherical harmonics. So if I have the gradient of the potential and take the gradient of that again, I will come to this equation, Laplace equation. Not Laplace, it's a divergence equation. And divergence of equation, and this some equation like it can be expanded in terms of Laplace tensor spherical harmonics coefficients, spherical harmonics like here. The formula is a little bit long, and I explain it here. If I have the spherical harmonics of the gravitation of the potential, then any function like with tau, theta, and lambda over the sphere can be expressed in this form. N from 0 minus 1, and I from 1 to 6. And here I have V and M. I is the potential of the function, and zeta I, theta, and lambda. This zeta are called, let me write TSH, this one, tensor spherical harmonics. And tensor spherical harmonics have this orthogonality property. If we have this integral, zeta and m, I, theta, and lambda, double dot product, zeta, n prime, m prime, I prime, theta, lambda, the sigma, will be, let me clean this part, will be 4 pi n, and I will explain this n later, with 2 delta n m prime, delta m prime, delta I prime. That is orthogonality. Of TSH. This is very important for transferring the spectral solution to a spatial solution, and also modeling the gravity potential or potential. So this spherical harmonics, this n value, is the, I can define it here for you. N is n. This formula is a bit long, but it's okay. But do not forget it's power 2. It could be 1 when I is 1. 1 over 2 n plus 1 when I equals 2. 2 minus n multiplied by n plus 1 n plus 2 I equals to 3. 2 into n plus 1 2 when I is 4. 1 over 2 n plus 1 I is 5. And 2n minus 1 n plus 1 n plus 2 when I is equals to 6. So these are the parameter in the orthogonality property, and the spherical harmonics themselves are when I is 1. The first one is the same with ordinary scalar spherical harmonic function, would be ERR. When it's 2, this will be derivative of theta lambda, derivative with respect to E zeta x, plus derivative of y and m, theta lambda with respect to sine theta the lambda E yz, and z3 and m theta will be this little bit long. Is operator function theta minus 1 over sine theta d lambda 2 y and m exx minus eyy plus 2 multiplied by 2 1 over sin y and m lambda theta lambda and exy. There are more, but I can just explain that if I apply this equation of the fourth one to the spherical harmonic expansion of the gravitational potential, I come to this formula. So I just write again the formula for the spherical harmonics. Let me write it again here. Let me see here. Minus 7, then I have r over r m plus 1 y and m theta and lambda, and of course t and m. So I can write this expansion like that. Tau up to 4 r theta and lambda will be minus n. Second order derivative of r over r plus 1 zeta 1 plus 2 r over r m plus 1 zeta and m2 theta and lambda plus 1 over 2 r2 r over m plus 1 and plus 1 zeta 3 and m, and n plus 1 over 1 theta 4. But actually what we need is this part. This part, not this part. This part, this part, and this part. We do not use this one. So the orthogonal, we can omit this equation. So in this case, we can write the derivative of the tensor of the gravitation in this way. Second order the radial derivative zz plus x z or t. You can write t instead. T ex plus 2 t yz eyz plus 1 over 2 t xx minus t yy exx minus eyy plus 2 y and xy exy plus 1 over 2 t xx plus t yy exx yy. And in practice we need this part again. How do we do that? Simply, you have the expression, a mathematical expansion of the spherical harmonics, and if we multiply this operator, this operator, this operator, and this operator to the spherical harmonic expansion of the tensor, then we can obtain 3 solutions. So this boundary value problem means that the potential is 0 and we have tzz at boundary value, ty, txx minus tyy and txy at boundary. So it is vertical, 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 horizontal, and horizontal, horizontal. How do we solve that? This one is easiest. What is tzz? Is a second order derivative of potential. Let me write it like that. T was n from 0 to infinity, m from minus m to t and m, r over r n plus 1 y and m. If I take the derivative of this equation with respect to z, which is r, I come to this formula. It will be it will be n plus 1 n plus 2 over r2 summation. I can write it again here. R2 r over r n plus 3 summation m minus n t and m y and m, or I can write z1 and m. Both are correct. So for the first part, the question is, if I have tz at satellite level up, or at the boundary, how can I determine t and m? So the solution is easy. So TZZ is now, and TNM is needed. So if I multiply TZZ, I put it inside an integral like this. I take the integral, global integral from TZZ up, and well, I will say Y and M, theta and lambda. There's sigma from the left, and I take the same on the right hand side. This means that I will take the integral of the right hand side. I come to this formula if I do so. This will be, I will write it, sigma, then 0, then n plus 1, n plus 2, r2, r over r n plus 3. And here, let me clean this part. I will continue there, down there. Then we will summation m minus n to n, t and m. And now the integral comes in, and one have already y and m here from the formula, and I multiply one the other. Theta prime of lambda prime, this sigma. So what is it? This is the based on the orthogonality properties of the spherical harmonic. It will be 4 pi n minus m n minus. And this summation will be non-zero when n is equal to n prime or m is equal to n prime. Therefore, all these things, this summation will disappear. Then I come to this formula simply. TZZ at satellite, NM, theta prime, lambda prime, the sigma will be m plus 1, m plus 2 divided by r2. Let me clean this one. R over n plus 3 and TNM. So what we needed is the spectral solution. We need TNM. And on the other side we have the second order derivatives. So solution of this equation for T and M will be what we needed actually. So the solution will be T and M is, oh, I have forgotten 1 over 4 pi somewhere here. 4 pi will be 1 over 4 pi R2 1 n plus 1 m plus 2 r over r n plus 3 integral of TZZ at the satellite level, theta prime lambda prime, y and m, theta prime lambda prime d sigma. That's the solution, or we can say vertical spectral solution. So the important thing here is that we need to have a global coverage of TZZ all over the globe in order to compute TNM. Another important issue that you need to know is that the second order derivatives are more sensitive to high frequencies. I have already discussed that because look at this expression for the TZZ formula. In the TZZ formula, we have had these formulas: R over R, or damping factor, n plus 1, n plus 2, and here I can write R2, it doesn't matter. So R is smaller than small r. This means that this ratio is smaller than 1, and when it gets power, it gets even smaller. But when it gets smaller, then it will kill the frequencies faster. The frequency killing starts from the low degrees. But when it is multiplied by these coefficients, n plus 1 and n plus 2 here, and it is multiplied by them, it will increase. When increase, this term is increased and will reduce the power of reduction of R over R. This is why this causes that the frequency killing or frequency reduction starts as at higher degrees. So let me compare this one with simple first order derivative, which is this one. And as you see here, it's pretty clear that the second order derivative that we have here has more powerful coefficient behind this damping factor here than this on right hand side here. So n plus 1 is weaker than n plus 1 plus n plus 2. And if we have the potential only, it will be this one. So you see that if we have this, if we have the potential, is for potential. Potential is the first derivative, and the second derivative. As you see, the map of this function potential is smooth, but for the gravity is not smooth, and it's not smooth, and for the second order it's not even, it's even more detailed. It's not smooth at all. It means that the first order derivative is smoother than second order derivative. So it causes that you can recover high frequencies of the gravity field by the second order derivatives, and you see more details because this coefficient which appears here doesn't let the damping factor to reduce the high frequencies too much comparing to the rest of them. And now let me back to this spectral solution. As you can observe here, we have a downward continuation factor. Downward continuation factor is in fact R over R n plus 3. So small r is larger than r. This means that this ratio is larger than 1. When it gets power, it will power n. It will start amplifying the frequencies by n. When it increases, the amplification increases. And the problem is that if you have any noise in the data, the noise will be amplified as well. So it means that the amplification will be much faster. And when we have n plus 1 and n plus 2 behind it, since they are in denominator, they will reduce the amplification power. So it means that you have more chance to recover high frequencies from TZZ. This is why this gradiometric mission, satellite gradient of GOES, has been launched. It is gravity field and steady state ocean circulation explorer. This GHOST mission has been launched. The main goal of GHOST was high resolution gravity field modeling. It means that they wanted to determine the gravity field to high degrees of N, up to 300 they could go from the space. But around 20 years ago, it was about 70, 50, something that I remember. Quite now, in the case that we are at the surface, of the sphere, it means that r, small r, equals large r. Then T and M will be again R2, 4 pi, 1, M plus 1, M plus 2, integral PZZ, theta prime, lambda prime, but this time TZZ at the surface, multiplied by Y and M, prime, lambda prime, So this also has the same property. If you have, because of the presence of this one in the numerator, these high frequencies of TZZ will be recovered better from TZZ, from the spectral solution. So this is a spectral solution. Now we go to the spatial solution. It's very simple, especially we want to get the potential, and I have the spectral solution. It's enough that I insert this spectrum inside the spherical harmonic expansion of the potential. How do we do that? Let me clean this part. I use this solution now. I write it like this. So it's T and M was here on the left hand side, if I remember, T and M, and I want this potential outside. Then I have a spherical harmonics expression minus N, and here I have T and M, Y and M. This is the potential spherical harmonic at the surface of the boundary, or at the boundary. This T and M comes here. Then T will be, I do not write M completely, you can understand what I mean. R2 over 4 pi will be here. 1 N plus 1 M plus 2. R over R M plus 3. Integral of TZZ, theta prime, lambda prime, and continuation here, lambda prime at theta prime, and I already have Y and M, theta and lambda. So I have this M, look at this summation here, and I have these two here. It will be addition theorem of spherical harmonics. Therefore, I can write this equation like that. So I write the potential at the boundary will be R2 over 4 pi summation and 0 to infinity, and I will write N plus 1, N plus 2, R over R, N plus 3. And now, instead of this summation over M and this product of the spherical harmonics, I write 2N plus 1 Pn cosine theta. cosine psi. And this should be inside an integral. T, zeta, zeta, theta, and lambda. But T is here at the satellite level. So then we are there. We have a special solution to determine the potential at the surface of the boundary, or at the surface of the sphere from the TZZ measured at a higher level than yes. But the issue is here that this downward continuation factor, as you see here, downward continuation factor. And as you see, this kernel function is not convergent. You cannot have a closed form formula, and you have to limit this to frequency to a specific number. Otherwise, you cannot get a solution. But in the case that R over R is equal to R, it means that the gradients are measured at the surface, and you want to determine only or smooth this function to bring it back to the potential, then simply you have this equation, this integral formula, which is 2m plus 1, m plus 1, m plus 2, Pn cosine, summation over n here. This sigma, TZZ, this sigma. Then you can determine however, this kernel function is not very well behaving. We will discuss that. Behaving. Maybe explain what is behaving later. So we have a special solution of the vertical gradiometric boundary value problem. Now, solution of vertical horizontal gradiometric BVP. It is very similar to the astrogeodetic boundary value problem. And again, potential outside the surface is required, and boundary values are Ax and Ay. So the mathematical expression of the issue is that we should compute this. You should use these boundary values to compute it. And then we have to use a vector spherical harmonic. So if you remember, Tx1, I will write it, xz plus t yz equals to. So I will write this equation like that. Summation n 0 to infinity. And I have formula for xz and yz. I will write it T and M. I will write R over Rn or summation M. And here I have a Z and M2. The vector or tensor spherical harmonics of the second type actually. And here I take the second order. If I take this one, z, and I apply this to the integral of this formula, I come to, if I remember, it was y and m theta along theta e x y, or y and m sine theta e y z. You have here, and the summation. This is the general spherical harmonic expression of that, and in order to come to a solution, I multiplied both sides of this one by the spherical harmonic, tensor spherical harmonic of second type in this, and take the integral. In this case, I can come to this formula. So I'll try to write a little bit smaller, lack of space we have here. So I write integral of txz exz plus tyz yz multiplied by double product z n 2 theta prime and lambda prime, the sigma equals to, now this term we multiply this one to again. However, we have also mathematical derivation. Let me see. Let me go and write it and make it clear. I should write that this equation, spherical harmonic, the formula for Txz is, if I write this formula for that, the Txz is actually 1 over r t theta minus 1 over r t r theta, and tyz is very much similar. It's r2 sine theta t lambda minus r sine theta t r and lambda. This is the mathematical formula for the gradients. And if we apply this operator to the spherical harmonics of like this, we have it in the spherical harmonic expression for y and m, and also this one, we apply this operator here, we will see that this will be simple. Let me take the derivative, you can see directly. Uh, 1 over r2, r I will take it outside, rho on the y with theta minus, this will be 1 over r actually, and it will be rho 2 on the r on theta. So this means that we have to apply this operator to the spherical harmonic expansion of t theta and t. If we do that, it means that if we apply this formula to this term, 1 over r theta minus y and m theta lambda. Och, and we have r plus m. So the first one, 1 over r, 1 over r, y and m theta minus r over r. If I take the derivative with respect to that, it will be plus m plus 1, and I have one r behind, okay, then it will be n y and m theta, and I don't have a space, r over r plus 1. Then therefore, if I take this based on this formulation, the tx not tx, the operator, I would say, this operator, if I apply it to the spherical harmonics, I will come to that one. It will be 1 over r m plus 1. Then it will be this r2, I would say, then r2. Then it will be 1 y and m theta multiplied by m plus 2. Similarly, if I apply this formula to for lambda, the operator for the lambda, I come to this formula. 1 over r2, r over r m plus 1, round y and m, round lambda, sinus theta, n plus 2. So, in this case, the spherical harmonic expansion will be summation from 0, 1 over r2, r n plus 1, n plus 2, and summation t n m multiplied by y n m theta plus y n m, then e x y, y n m around lambda sinus theta. So now if I multiply, then z and m 2 theta and lambda, that's. Then it will not be difficult to see that this term is also z2. And by this integral that I take from both sides, I will see that this is orthogonality. Of TSL. This will be the red bar, 4p delta n prime, mn prime, multiplied by n plus 1. Based on this, the integral will be simplified to this term. Sorry, the right hand side will be simplified to was 1 over r2 r m plus 1 multiplied by t and m 4 pi delta n prime m prime, and we have already already have n plus 2, and now we get n plus 1 and plus 2 based on the orthogonality. So that's all we order. This means that the final solution will be for T and M means that the potential T and M will be 1 over 4 pi, again R2 I will write, divided by m plus 2 n plus 1 n r over r n plus 3 integral of txz multiplied by 1 n theta plus tyz around y and m sine theta alpha. So this is the solution, your spectral solution. And as you observe here, n cannot be 0 because if it is 0, it will be singular. This means that you cannot recover the zero frequency of the potential from the first order derivative. Now I transfer this solution to the spatial domain. It's very similar to the Wenning-Manes or the strategetic undervalue problem. Just we use the addition theorem with spherical harmonics. If I insert this back to the spherical harmonic expansion of T is spherical harmonic of T is summation T and M, Y and M, theta and lambda. So if I insert this T and M back here, and I simplify the formula, I come to this integral equation. I will do it directly. If I write it down like this is VB0, n cannot be 0, if I will start from 1, then I will have 2n plus 1 over n plus 1 n plus 2 r over r n plus 3, and here I will have Pn, the lemma from the psi, and here I write, if you remember the last lecture or previous lecture, I will write the rest here for you. Here I will write Txz cosine alpha minus Tyz sine alpha. That's the integral solution of this. This kernel is not isotropic. Isotropic kernel is not function of azimuth. Since we have alpha here, this is azimuth. Therefore, this kernel is not isotropic. It is function of azimuth. But this part of the kernel. This part of the kernel is isotropic. Isotropic. So you have a mathematical model now, integral solution for converting vertical gradients to the potential at the surface of a sphere. So, and if R is equal, then it will be much easier for you, and it will be, this term will be 1. Then you will come to this. So this was the vertical horizontal special solution of the vertical horizontal gradiometric boundary value problem. Now we go to the solution of the horizontal solution. That's not dollar, it's solution. It's a solution of horizontal gradiometric BVP. So the principle is totally the same, it's completely the same, but the main difference is related to how the mathematical tools are applied here. So if we look at it, the boundary value problem, we need the potential, and we have Txx, Tyy, and Tzz. Yeah, Txy, sorry. So I will write directly the solution. It is a little bit long. It will be R2 over 4 pi. It will be 1 n minus 1 n plus 1 n plus 2 r over r n plus 3 integral of the integral we will like that Txx minus Tyy multiplied by E xx minus Eyy, and then it will be 0 plus, and it will Txy Exy multiplied by Z3 and M. Yes, sigma. Here I have used the orthogonality properties of tensor spherical harmonics. Let me check the formula. It should be -2 here. -2 here. And if you go to the you can go to the spatial domain simply from this formula. And if you come to this solution, and the spatial solution will be potential R2 over R integral of, then here is from 2 1 over n minus 1 and m plus 1 m plus 2 r over r m plus 3, and inside the integral I have Txx minus Tyy multiplied by a big equation, actually. A big, if you multiply it by is very long, and I will try to simplify it for you here. Write this like that. The proof is in my book. I have proved this cosine 2 alpha minus v and v not v t xy sine 2 alpha. And here we have Pn2 cosine 2. So I'm not going to go to too much detail in mathematics. It's long and complicated, and what you need to know here for the boundary value problem. Look at this term. When n is 0 and n is equal to 1, this will be singular, this kernel. And this means that you cannot recover. You cannot recover 0 and first degree harmonics, I would say, degree harmonics from HH derivatives. HH derivatives. And again, you see, this is downward continuation factor. Let me with another color. This is downward continuation factor. It is strong. Is a strong amplifier, but these terms which are here, they are also strong. It's m with power 4. Then they will reduce the power of it. But of course, it depends how smooth is this function too. So consider that this kernel is also isotropic. It's not isotropic because of involvement of this alpha azimuth, but this part we call this isotropic part of the kernel. So this is the boundary. We have 3 solutions for boundary value problems. Gradiometric boundary value problem. Let me summarize them. So I will say gradiometric BVP. It has 3 solutions: VV solution, VH solution, vertical, horizontal, and horizontal solution. VV solution, all of them have a spectral and a spatial solution. All frequencies can be recovered. Here, all frequencies except, I would say that, let me write it simpler. Now, all frequencies except n equals to 0. It means a 0 degree frequency cannot be recovered. And here, all frequency except n, 0, and 1. So, but if you determine the disturbing potential is already from degree 2, so it's no problem to use this horizontal term. But for example, if you want to determine the mass of the Earth, which actually includes this 0 degree harmonic, or center of this, and the center of coordinate system, which is the first degree harmonics, then you cannot recover this from the horizontal. And the 0 degree harmonic, which is the average value of the function of the gradient over this sphere, you cannot recover that one because this is 0. It's blind to the 0 degree harmonic. 0 degree harmonic is an average of the function of it. So we have a spectral solution and we have the spatial solution in all types of boundary value problems. So it depends. If you have a spectral, if you have global data, you can use a spectral solution. For example, satellite data normally have global coverage. So you can use them for determining the spherical harmonic coefficients. But the local data you do not have, then you have to go back to this to the integral solution. But if it depends on the behavior of the kernels, so which I'm going to explain this here. Kernel behavior. Let me write in British English. All these mathematical or special solutions that we have done, we have discussed here. We have a function from on the left-hand side. We have one double integral on the right-hand side, and we have a function. Let me call it k, which is a function of psi. Psi is the distance between 2 points. So let me draw it. And I have another function here. Another. Let me call it j instead of f. G, theta prime and lambda prime, the sigma. So let me draw a figure here, and again I will emphasize that if it is point is theta and lambda here, from theta and lambda, theta is this, and it will be theta prime and lambda prime. This angle will be lambda prime minus lambda, and this special angle along this from in front of this camera is psi. So this kernel function is between theta and lambda and theta prime and lambda prime. So these are called integration point, and this one is computation point. So this is computation point, what we are going to compute, and this one is integration point, then what we are integrating, the point that we are integrating. Then I always say that you can use local data by integral formula, but the question is if we can do that or not in reality, in practice. It depends on the behavior of the kernel. What means the behavior? Let me draw the behavior of one kernel for you. For example, I have a kernel function like this. 0 up to 180 degrees, and this is psi value of the kernel, and this is the k value of the kernel. The kernel starts from up above and goes up to. So do you see that this kernel function is like that, has non-zero values up to 180 degree 180. It means that it has value for that. And we have, let's see, we have another kernel which is like that. It goes down up to here and goes down to 0 fast. And we may have another kernel which is like this, and this continues to them. What is the role of the kernel? Kernel is a weight function. It shows the importance of far zone data. For example, here in the blue curve that I have, you see that the kernel doesn't get close to zero or even up to 180 degree. It means that the data for this type of kernel are still important even if they are far from the computation point. Let me see that the computation point is here. I can say computation point. And here the places that psi is here. This is the 0 is computation point, and there is our integration point. So if we solve this, if we have that this integration point is far from the computation point, you see that they have influence on the result because they are not 0 here. But look at the green curve. The green curve get closer to 0. It means that 0 is here. This is the contribution of the data after this place is 0. Then you do not need to use this data out after this degree. They are not important. And look at the orange curve. It's even closer to the computation point. So if this is a good kernel for regional studies or not, it depends on the behavior of the kernel. Not all integrals are suitable for local integration. Not all. It depends on the behavior of kernel. If the kernel is sharp, like this, like the orange one, and get closer to 0 and to the end, to the point, this is called well behaving. It's well behaving kernel. This is the thing that I named it actually in 2011. This type of kernels are easier because this shows that the kernel shows that the contribution of the data after this point, when it gets close to 0, is insignificant. So you do not need to have a global coverage of the data. You just need the data which are up to this distance from the computation points. For the green one, you need more data. You need larger data over the computation point. And for the blue one, you need the whole sphere. Let me draw a figure here for you to explain this concept in 3 dimensions. So this psi is that psi. You consider the psi. I have this the whole sphere, and I have the computation point here. And consider that I have the blue kernel, and as you see, this distance up to 180 degrees. It means that I am here now. Other side of the sphere, the other side of the sphere. The other side of the sphere, here, the data up to that point are significant. Let me draw a cap, which is psi. This is this point. This point is here. This means that if I am at the surface of this sphere, and I have the data all over this area, they are all important and significant, and I have to use them for integration. But outside, no, it's not important because the kernel gets closer value to 0. And the orange one, this integration area, which I show it by psi here, I just need the data over here. And data outside here are insignificant. So in order to see if a kernel is suitable for local application or regional application, you need to look at the kernel behavior to see if they are well behaving or not. How well behaving are they or not? This is one issue that you need to consider for using the input. Now let me explain the difference between the first, second, and third order derivative. For example, if I have t function, I have tr and t, let me see, tz or tz, tr is the same. And here I have this factor r over r. This is smooth. And here I have m plus 1 r over r. And here I have m plus 1, m plus 2, and r over r, m plus 1 divided by r2. If I plot these kernels based on these damping factors, well, what does it mean, damping factor? It means to kill frequencies. When you mean to kill frequencies, I have the degrees up to 180 degrees as psi here, and I have here. And if I have this kernel, for example, this Poisson kernel, and I have Pn here, Pn cosine, what does it mean? These 2m plus 1, let me write this kernels clearer so that you can see the differences. It's not bad, this was not good. So, I will write it in a uniform for you, so more comparable. So I will write this integral, and I have a kernel, and all of them have 2m plus 1 here, and are r over r, m plus 1 here. And for the potential, I have 1 here. For the second order derivative, I have m plus 1 over r here as well, minus. And I have m plus 1, m plus 2, r2. And at the end, I have Pn in front of all of them. So, as you see here, and consider only the first part. The first part which is related to T, and the one TR and TRR, the third one. Okay, that's the potential. So this means that if I have Pn is comes up to infinity, and this one is not killing the frequencies actually that strong, that means that if I plot the kernel will be like that, very smooth. The Poisson kernel at the high altitude, high altitude. And when R increases, it will be even smoother. For example, if you are close to the surface of the Earth, the kernel behaves like this. For example, let's say R is 10 kilometers, and second R is 100 kilometers, and R is 1,000 kilometers. When you are at the surface of the Earth, the kernel goes fast to zero. What does that mean? When you are at when you are at the surface, it goes close to zero. Why? Because R is closer, this large R is closer to a small r. Then it is close to, this will be very close to 1. It means that it will not kill frequencies. And you will have high frequencies then. When R is getting slightly larger, if we go to the 100 kilometers, then we'll start killing the frequencies. Then we go back and it will be smoother. And when you are at 100 kilometers, even wider. This means that when you are at high frequency, when the kernel, when R is considerably large, then it will start killing the frequencies. Then when you get far from the surface, you will see more of the global nature. It is the same principle that I explained. When you have something close to your eyes, you will see the details. And it's like that. If it is R is 10 kilometers, this small r is closer to the value of a small r will be closer to the large capital R. And this ratio will be closer to 1. Then you will get high frequencies. you can see the high frequencies because you are closer. Then in this case, the kernel will be sharp. And when R increases, this ratio will be far from the 1. As we get smaller, and it get the power, then it start killing high frequencies. Then this will be smoother. The kernel will be smoother like this. And when it is at 100,000 kilometers or even higher, then it will be then the contribution of data. It is exactly what I explained. When I have the surface and I am close to, I see the see from the close distance, or I watch to see the globe from the higher distance, and even the highest one here. So it's the distance of a 10 kilometer or 100 kilometer or 1,000 kilometers. So what do you see? If you are here, you cannot see here. But if you are here, you see here better. You can see that. And when you are here, you can see the whole. The field of view is limited. This is exactly the same. This kernel, if I rotate this system, it will be like this. I mean, let me redraw this figure, this curve again. So if I have, for example, 100 left and 100 right, this side, I have. If I have high frequencies, then the kernel is behaving like this, fast, get closer to zero faster. For medium frequencies, it will be like this, smoother. And for high frequencies, it will be like this. So it gets closer to zero, it's low height. So this is the relation between the kernel, this R over R, and the shape of the kernel. Now, let us look at this kernel based on the derivative, the first derivative now. What will happen with those the example again from R 10 kilometers, R is R plus 10 kilometers, R is R plus 100 kilometer, R is R plus 1,000 kilometers. In the second case, let's say the second case, I consider this one, or n plus 1. So what I have here is n plus 2 and n plus 1. But 2n plus 1 was common with both of them, or all of this kernel, then I will ignore it. I just consider 1 over n plus 1 multiplied by R over R. So n plus 1, when it is close to 1, when at the case, it will be sharp. It will be sharp and close to 1, but it's less lightly, it is very close. And it will start killing the frequency, but this one is multiplied to this one. It gets it a little bit larger, then behavior will be like that. And again, when it gets like that, the behavior will be a little bit like this, the higher, but when it is higher, when you multiply n plus 1 to this small value, this small ratio, then it will be a little bit sharper. And for 1,000 kilometers is the same again. But the issue is that here, since you have n plus 1 behind R over R, this kernel will be sharper than the case that you use only R over R. So it means that the killing high frequencies are started at higher degrees. This means that the kernels are sharper. Then you need less data around the computation points. And in the case that you use the second order derivatives, let me with another color. This, oh my God. In the case of using second order derivative, this amplification will be even higher, like this. Maybe like this even, go up. So the behavior of kernel is very important, and I would say that more derivative, more localized. More localized. For understanding the concept, just I explain in another way. I have a kernel like this, and I have a kernel very sharp like this, and I have a kernel which is a smooth kernel. And I have some signals with some frequency. So which one can model this smooth function? Of course, the smooth kernel. And if I have a frequency like this, a signal like this, which kernel can present this frequency better? This one. Now consider I have such frequency. Which kernel can present this better? This one, because it is sharp. We see it here, can model it here. But if I use this kernel for this, you see it doesn't work, cannot fit. This kernel is too sharp for that. But if I want to, for example, do this, use this smooth kernel for modeling this sharp behavior, you see this kernel cannot present the small variations. And also this. So this means that the kernel behavior is very important. If it is sharp, it can model the high frequencies better. When it is smooth, not sharp, then it cannot model the high frequencies. So we have another type of kernel. The behavior of that kernel is also similar to the other one, the other kernel that we have discussed now. But these kernels do not start with a high value at the computation point. They are like this. I call this kernel bell-shaped. They are like a bell. And we have psi here, and we have computation point here, and the kernel value here. The problem is that around the computation point, they are important. They are not important, but for around the zone at a specific distance from the integration point, they have higher weight than the other parts. For example, if I am at the surface of the sphere, and this is integration point, and this is the total integration domain around the point, and the data here, data which are here are important. Not even those closed. So when these type of kernels are seen, when we have derivative with respect to psi. So when you have derivative like that, then this type of kernel appears. So the contribution, the close to the signal, they are like this. They are small, the zero contribution. They increases the contribution down. And so this type of kernels is they are a little bit different. They are not very well. They are not quite well behaving. So it's very hard to work with them for inversion. But for integration, that's fine. If you want to see how much you have to consider the contribution of Farzone data. You just simply say, look at this when they go up and down. Don't care about it. Then to see when they go down to 0. Then that will be your limit. Up to here. So you will consider up to this level. That's fine. You shouldn't care about when it's go up and down. If it is close to 0, update a while or not. Then you can. But for inversion, it will be difficult. Inversion I will teach you later about integral inversion. But this type of kernel are called base shape. For example, the kernels that you use for astrogeodetic data, let me write them here. Astrogeodetic BVP. Here, gravimetric, vector gravimetric BVP, and gradiometric BVP that we have had TXZ, TYZ. Here we had TX, TY, and here we have also derivative of the geoid, actually, geoid with respect to X and Y, or phi and lambda. In all of these type of kernels, we have this term, the kernel function. If you remember the mathematical model, the psi, and we have had the quantity, it could be n, could be tx, could be txy, and we have had cosine alpha plus minus nx and ny, ty, tz, tyz, sine alpha. So what does it mean? It means this. These kernels are non-isotropic. When they are non-isotropic, they are normally bell-shaped. When they are bell-shaped. Again, the problem of the what's called the height is also valid here. For example, if I have this, if R over R is large, R over R, the kernel will behave like this. If R is small, then the kernel will be sharper, and when it is smaller, it will be even maybe sharper. So again, the problem, the relation with R over R is at the same, but the shape of the kernel will be like that. They are isotropic. They are not isotropic here because of cosine and sine. So these are the called bell-shaped kernels that you need to work with them later.